One situation where the conservation of momentum is very valuable for understanding motion is what happens in a collision. A collision is when objects crash into each other. To be a little more formal, I'll say that a collision is an isolated event in which relatively strong forces act between two or more objects for a short period of time. I'm not sure that's much better, but the point is that we have two or more objects approaching each other, then something happens, they crash into each other, and then afterwards we look again and see the final momentum, the final mass and velocity. Mostly we want to be able to clearly define the condition, the velocity of the masses before the collision and the velocity and masses after the collision. Say if we hit a baseball with a bat, it's pretty clear that before the bat hits the ball, that's the initial condition, so the mass and motion of the bat and the ball are your initial momentum. You have a brief moment of contact between the bat and the ball, so that corresponds to the collision, and then the trajectory of the ball and the trajectory of the bat after the collision, that corresponds to the final condition. The collision doesn't actually have to be a crash. Say an asteroid that moves through the Earth's atmosphere, or the gravitational field, I should say, deflects its motion, and that could be considered a collision as well, since there is a force acting between the two that is pretty strong when they are close together, and it's kind of small when they are far apart. We tend to categorize collisions into two types. One is an elastic collision. So in an elastic collision, the kinetic energy of the objects colliding is conserved. Energy is always conserved, but in many collisions, some of the kinetic energy is converted into heat. In the case of an elastic collision, none of the kinetic energy is lost to heat, it's all kinetic energy. In an inelastic collision, the kinetic energy is not conserved. Some of the kinetic energy has been converted into heat or sound. In a perfectly inelastic collision, the objects that have collided stick to each other, and they move together after the collision. So in this, we have a perfectly inelastic collision. The final objects have the lowest possible kinetic energy while still maintaining the conservation of momentum. Notice that in all collisions, momentum must be conserved. That's non-negotiable. However, kinetic energy may be converted into heat or sound, so it's only conserved in the case of elastic collisions. In the case of an elastic collision, both momentum and kinetic energy are conserved. In general, elastic collision problems are a little too much math for this course. However, we want to understand in general what happens in an elastic collision. So if we know the initial velocities and mass of an object, then we can set the initial kinetic energy equal to the final kinetic energy. That gives us an equation with two unknowns, the final velocity of both object 1 and object 2. We also know that the momentum must be conserved, so we can set up a second equation where the momentum of object 1 and 2 add up to be the final momentum of object 1 and 2. That means that we have two equations and two unknowns, so we can then solve this equation. When we do that, we find an intriguing result, that the velocity of 2 minus velocity of 1 is equal to minus 1 times the initial velocity of object 2 minus the initial velocity of object 1. That means that in a perfectly elastic collision between the objects, the difference in the velocity before and after the collision is the same. So this is often framed as the speed of recession is equal to the speed of approach, where the speed of approach is how fast the objects move towards each other, while the speed of recession is how fast the objects move away from each other after the collision. The classic example of this is on a pool table. So if you hit a cue ball with no rotation into a second ball with exactly the same mass, they must have the same relative velocity before and after they hit each other. The simplest way for this to occur is if the cue ball comes to a complete stop and the ball you hit now moves with exactly the same velocity as the cue ball started with. So notice that the kinetic energy here is exactly the same before and after, since the initial velocity of the cue ball and its mass is exactly the same as the final velocity of the ball you hit, and it has the same mass. The cue ball ends with zero kinetic energy, just like how the ball you hit, that started with zero kinetic energy. Notice I've neglected the rotation of the pool balls, so if there is spin, then things get much more complicated. But if you hit the ball completely flush, then there should be a very little spin on the ball, and the cue ball only move a short distance, so it will not have much time to pick up rotation because of friction over the felt. So this sort of analysis should be reasonably accurate. Elastic collisions get more complicated when the masses are different, but the key is this relative velocity between the two objects is exactly the same before and after the collision. This slide shows the formula for the case where one object collides with a second object that is at rest. So notice that if the mass of object 1 and the mass of object 2 are equal to each other, then the final velocity of ball 1, the cue ball, is mass 1 minus mass 2, so it is 0, and the velocity of ball 2 is 2 times the mass of 1 divided by the mass of 1 plus mass 2, so the final velocity of ball 2 is equal to the initial velocity of ball 1. So if the masses are equal, it's the same. And notice this, you have the same velocity, so that means that your speed of approach and your speed of recession are exactly the same. The other case of interest is if the moving ball is much heavier than the ball that hit it. So then its velocity is pretty much the same as the original velocity, and the velocity of the ball it hits is 2 times the velocity of the original ball. Notice the speed of approach is the velocity of object 1, so the light object that was hit needs to move at twice the initial speed of object 1 so that the speed they move away from each other is equal to the speed of their approach. If the struck ball is much more massive than the incoming ball, then the incoming ball just bounces off the ball it has struck, and then it heads back in the direction it came from with the same velocity that it started with, while the ball that is struck barely moves. Here again, the speed they move away from each other is the same as the approach. The heavy ball is almost stationary, while the light ball bounces off and moves in the direction it came from at roughly the same speed it approached. The key here is that in an elastic collision, the speed of the two objects approaching each other is the same as the speed at which they move away from each other. Okay, so I've coded up 2 questions here. So one is a comparison between elastic and inelastic collisions. So you'll want to use conservation of momentum to understand the question. And the second is a qualitative look at some elastic collisions. Good luck.